In this video, we will learn about the activity series of metals and how to use the activity series of metals to predict if a redox reaction will occur. So our redox reactions are typically spontaneous in one direction. That means that it will just happen on its own without an external force. We don't have to put in energy to make it go. It will just happen. And so this is an example of zinc solid being put into aqueous copper 2+ solution. And when we put that zinc solid in, then the copper gets plated onto the surface. So we have solid copper plated onto the surface, and then there are some zinc 2+ ions in solution. There are still some copper ions in solution because we didn't use up all the copper ions. But there's copper plated on the surface. And so this direction is spontaneous because it just happens on its own. But what happens if we try to do the reverse reaction? Let's take zinc 2+ solution and add in copper solid. And so we have that over here. So if we have zinc 2+ aqueous and we put in copper solid, nothing happens. There's no reaction at all. And so in one direction, the reaction is spontaneous, and in the other reaction, it's not spontaneous. If we wanted this reaction to occur, we would have to put in more energy and external force in order to drive that reaction in that direction. So some reactions are energetically favorable, and they will just be spontaneous. They will happen on their own. Just because it's spontaneous, it doesn't say anything about the reaction rate. The reaction rate can still be very slow if the activation energy is large, but they are still spontaneous. They are still energetically favorable. It doesn't say anything about the rate. And so we're just trying to decide which direction is energetically favorable, and so which direction will occur. And so we know that in a waterfall, water always flows down. Water goes from being very high up, which is high potential energy, to being low potential energy. And so our electrons in our reaction are similar. They're going to try to go from a high potential energy state to a low potential energy state. And they'll do that by changing which element they are sitting on. And so this process of water flowing down a waterfall only happens in one direction. Our cell phone batteries, we know that batteries run on redox reactions. Batteries in our cell phones always discharge spontaneously. We never have a battery spontaneously charge. It only spontaneously discharges. And so we have to put in energy in order to make our cell phones charge. That only happens they discharge spontaneously, and then the reverse process is not spontaneous. So this is what's known as the activity series of metals. It's just a list of metals and hydrogen that you can find on the internet. Alex has it in the data tab on Alex. They have a very detailed activity series on Alex in the data tab. So you'll have to click on that icon to open it up when you do your homework. But how this list is organized is the most easily oxidized metals are listed at the top. So lithium is very easily oxidized. That means it's going to be very easy to remove this electron from that lithium. On the other hand, gold is not easily oxidized. It is the least easily oxidized on this list. That means it's going to be very difficult to remove these 3 electrons from the gold. For a reaction to be spontaneous, the oxidation half reaction has to be higher on the list than the reduction half reaction. So if we look at this, it's always listed in terms of oxidation. So we'll have to find our oxidation half. Must be higher than our reverse reaction. And so for reduction, you got to read on the other side. So that's not how you spell reduction. So you got to find your reduction half reaction by looking in the reverse side. So higher than reduction half reaction. Okay, let's do an example. Oh yeah, so that's our reduction half. So gold is, the gold 3+ ions are the most easily reduced. We have to remember that reduction is the gain of electrons. We can't make gold neutral gain 3 electrons because then it would be a gold 3- anion. Instead, we have to add those 3 electrons to the gold 3+ ion and then turn it into gold neutral. So gold 3+ is the most easily reduced, and neutral lithium is the most easily oxidized. Okay, so here's our activity series again, and so I have to find my oxidation half and my reduction half in order to predict spontaneity. I actually wrote this on the previous slide. So let's see how this works out. So when you're reading the activity series, you have to look at your problem and you have to find these things on the activity series. So let's find Zn solid. And so here is Zn solid. And so Zn solid is on the reactant side. And it would turn into zinc 2+ aqueous plus 2 electrons, which is oxidation. And now my copper 2+ ions. Where are my copper 2+ ions? Here's my copper 2+ ions. And so those are on the product side here, but I need them on my reactant side. So that means I got to flip this around. And so I need my copper 2+ aqueous ions and my 2 electrons. And those are going to form Cu solid. And so that is gain of electrons, and so that's my reduction half. So this is my oxidation half, and this is my reduction half. And so since my oxidation half reaction is higher on the list than my reduction half, then my reaction is spontaneous. And so since this reaction is spontaneous, I can combine my 2 half reactions in order to get my overall reaction. And so my overall reaction will tell me my products. I will form zinc 2+ aqueous ions and copper solid. All right, let's apply this to the reverse reaction. Let's find our zinc 2+ aqueous ions. Those are here. Those are on the product side, but I need them on the reactant side, so I have to flip this around. And so I have zinc 2 plus aqueous plus 2 electrons, and that's going to form Zn solid. And it's gaining electrons, and so that is reduction. And so this is my reduction. And then I have my copper solid, copper solid, copper solid is going to turn into copper 2 plus aqueous ions plus 2 electrons. And so that's my oxidation half. But since my reduction half reaction is higher than my copper reaction, my oxidation half reaction, this reaction is not spontaneous. So the oxidation half reaction is lower on the activity series. This reaction is not spontaneous. No reaction will occur. All right. So there are real-life implications for this activity series of metals. And so as you can see down at the bottom of this list, gold and silver are very difficult to oxidize. And so that in part gives them their low reactivity in air. They don't oxidize very well. Gold and silver, hard to oxidize. So gold and silver are hard to oxidize, and so that is in part why they are very valuable metals. They resist corrosion. Also, everything that's above this line dissolves in acids, while metals below do not dissolve in acids. And so here's our H plus ions. And so this, going this direction, would be reduction, and that would turn into H2 gas. And so in our stoichiometric gas production lab, we reacted magnesium metal to make magnesium 2 plus ions. It was magnesium chloride in that particular lab. And so that's my oxidation half reaction, that's my reduction half reaction, and that produced H2 gas as a product. And so we did that reaction for our gas production lab. But any of these metals would have reacted with the acid to make H2 gas and some salt. These metals below here do not react with acids. Nitric acid does dissolve copper and silver, but that's thanks to the nitrate ion, not the H plus ion. So here's a practice problem for you. Go ahead and pause the video and see if you can work it out. You're supposed to be predicting the products and balancing the equation. If no reaction happens, then you should write no reaction. Okay, hopefully you have an answer. If not, you should be pausing the video, working out. All right, let's work this out. We have magnesium, and we have, this is chromium 2 plus, no, not 2 plus, that's 3 plus, chromium 3 plus ions. Each nitrate is 1 minus. So that's chromium 3 plus. Let's find chromium 3 plus. And so my chromium 3 plus is going to be getting reduced in this single displacement reaction. And so if this reaction did occur, magnesium would become a 2+ ion. That's why it says 2+ over there. But nitrate's a 1- ion, and so I would need 2 nitrates if this reaction occurs. But let's discuss whether it does occur or not. My magnesium would be changing from magnesium to magnesium 2+ in the single displacement reaction. That is oxidation. And so this is my oxidation half. And my chromium is going to be changing from chromium 3+ to chromium solid, neutral. And so that is going to be my reduction half reaction. And so this is going to be spontaneous because my oxidation half is going to be higher on the list than my reduction half. That's not how you spell spontaneous at all. So now that I know this reaction is spontaneous, I need to finish balancing my equation. So I got my chemical formulas, but I got to work out how many of each I need. I know that I need to lose as many as I gain, and so I'm going to need to multiply this by 3 and this by 2 in order to get 6 electrons exchanged between these. That way the number of electrons lost equals the number of electrons gained. So I'm actually going to need 3 magnesium, and I'm going to need 3 magnesium 2+ ions, and so I'm going to put a 3 there. And then my chromium, I'm going to need 2 chromiums. 2 chromiums. And so I just worked out my coefficients, and then my nitrates should be balanced. I have 3 times 2, and so that's 6 nitrates, and then 2 times 3 is also 6, so that's 6 nitrates. So I'm balanced there. Let's change colors and do the next one. So for our next one, we have copper and sulfuric acid. And so copper is down here. Copper would change into copper 2+ aqueous plus 2 electrons. And then my hydrogen would go from H+ in my acid to H2 gas. And so that's that half, and it would go that way. And so that's my reduction half, and this is my oxidation half. And so since the oxidation half is lower on the list, this reaction will not happen. All right, no reaction. I'm going to abbreviate that as reaction. Reaction is RXN. Okay, and now the last one. We have our aluminum. Let's find aluminum. No charge on the aluminum. Here's my aluminum. I change colors. Ugh. Not what I meant to do. Okay, so aluminum is here. It's going to go that way. And so aluminum would form aluminum 3+ ions and 3 electrons if this reaction occurred. Then my iron 2+ ions are here. And so that would be the backwards half. That would be reduction. And so iron 2+ would require 2 electrons in order to form iron solid. And so the oxidation half is higher than the reduction half, and so this reaction is spontaneous. And so we need to finish balancing this equation. Again, if I look at the number of electrons lost, that's 3 electrons, that's 2 electrons. So I'm going to have to go up to the lowest common multiple, which is 6 electrons. I need to multiply that by 2 and that by 3. And so I'll end up with, I'll just start from the beginning, distribute out 2 aluminums plus 3 iron 2 pluses. I know my electrons will cancel out. And so then in my product side, I'll have 2 aluminum 3 plus ions and 3 iron 2 plus ions. Not iron 2 plus, 3 iron solid. So there's my balanced chemical equation. You can double check that it's balanced by making sure that you have 3 irons on both sides, 2 aluminums on both sides, and then the sum of the charges on the product side is 2 times 3, which is 6 plus, and the sum of charges on the reactant side is 3 times 2, which is also 6 plus. And so this is charge balanced as well as atom count balanced. All right. Corrosion is the oxidation of metals. So anytime you see like rust on something, that's oxidation that's occurred on the metal. The process for iron rusting is actually several steps, but the first step involves iron reacting with oxygen gas and water. 4 electrons are exchanged. You actually form iron hydroxide first, but the iron hydroxide reacts further in order to form iron 3 oxide. So that's iron, and that's a 3 plus charge. And then you have 2 of them, and then oxygen is 2 minus. So you go from being iron 2 plus to iron 3 plus before you get this orange color. And so all the orange spots on here are that iron. It's named iron 3 oxide because the 3 in the name refers to the charge. So iron oxide, the iron 3 oxide, the Fe2O3 compound, iron rusting is known to be bad for the metal because this oxide layer flakes off, and that exposes new iron underneath, which can oxidize. And then that iron oxide flakes off and exposes more iron, and eventually it rusts all the way through. But not all oxides are flaky in texture. So even though iron oxide is flaky and flakes off, that's a detrimental oxide. There's other oxides that are protective and form a very hard surface that protects the metal underneath from further oxidation. Copper and aluminum have protective oxide layers. And so on the surface of this aluminum can, there's a very thin layer of aluminum oxide. And so aluminum oxide would have that chemical formula. The Statue of Liberty is made out of copper, which is the same metal as pennies, but it's blue in color, which is indicative of copper 2 plus ions. And so that green color of the Statue of Liberty is a more complicated patina. There's a video on Canvas you can watch about exactly what salts and other things are part part of that blue patina. It's like copper sulfate, I think, and then copper oxide. It's complicated. There's a video. So since some metals oxidize easier than others, there's ways that you can prevent metals from oxidizing if you don't want them to. One method of preventing oxidation is to use what's known as a sacrificial anode, which is a cheap metal that you don't mind sacrificing to prevent the oxidation of something else. So, for instance, if you have a piece of magnesium or a piece of aluminum, those will attract the or give up their electrons a lot more easily in order to oxidize, and they'll prevent the oxidation of iron. So this chunk of magnesium or aluminum is bolted onto this bolt in order to prevent the oxidation of the iron in the hull. Also, metal fences are often galvanized. Galvanized involves coating it with zinc. Zinc is higher on the activity series than iron, and so it will corrode in place of the iron.